In previous video, we looked at heat and wave equations and have found that in order to find its solutions for initial value problem, it was convenient to decompose the solution into signs, into sum of signs. It would be convenient to, it was convenient to read off the answer. So in this video, we'll learn that in fact, well, almost all functions can be decomposed into sines and cosines. So let's review the idea of periodicity. So a real valued function f from R to R is called periodic with period t if f of x plus t is equal to f of x for all x. So some functions are periodic with period 2 pi, sine x, cosine x, their combination, shifted function, and so on. They're also periodic with respect to 4 pi, right, or 8 pi, or 24 pi, and others, right? But we say that 2 pi is the fundamental period of these functions. Like it's the smallest value of that capital T from the previous slide for which the periodicity holds. Well, often we're interested in the behavior of some of these functions in some finite region of space, say a segment from 0 to L, along which the string is stretched, or along which the heat is flowing. So perhaps the most natural thing to do would be to consider functions that are only defined in this region because we don't really care what's going on beyond that region. Like it's beyond the sort of scope of that physics experiment that we are considering. So like this, right? There's a function that defined on a segment of length L. We will see that it's more convenient to instead consider functions that are defined everywhere on R, but are periodic with period L. So we'd simply take this segment and then we just periodically replicate it infinitely many times, perhaps by it may result in those junctions and discontinuities at the boundaries of the segment. So that's the first step in understanding the Fourier series. Then let's start out with a function which we call f bar with domain 0 to L. So this is the so we get the function with the domain of R just by setting it. It's f, which they refer to the previous picture, is f of x plus whatever multiple of L is required to put it into 0 to L. Like this. So this will be function f bar. Yeah, so as we discussed, there might be discontinuities. And that's okay because we'll allow ourselves functions with finitely many of those. So given a periodic function, let's say with a period 2L, we'll try to express it as a sum of the periodic functions we know have period 2L. So sine pi n over L x and cosine pi n over L x for positive integers, and perhaps the constant function. So such expression is called a Fourier series. Intuitively, the idea of the Fourier series is that from very far away, the graph of a periodic function just looks like a straight line, some constant function. So if you really kind of zoom out very far, like make it really small and tiny. And then subtracting off this constant and zooming in, we see oscillations at with some characteristic frequency. The simplest such oscillations look like sine and cosine waves, and we can estimate the function by those. And then we subtract those off, zoom in further, and then repeat the process, right? On the second step, we need sines and cosines of twice the arguments, and then subtract those, look at sines and cosines of thrice the argument, etc., etc. The above description is iteratively subtracting of successive approximations. May remind you talking about the Gram-Schmidt procedure, right? So orthogonal projections and understanding what will be the orthogonal projections to given bases. So our first step is in finding an inner product of the space of functions with respect to sine n pi l over Lx and cosine n pi over Lx, and the constant functions are orthogonal. So we need to establish the inner product to claim this statement. And fortunately, it's more or less given to us, right? We don't have to work too hard. So here's the theorem. So you simply integrate just for symmetry, let's consider this as a segment from negative L to L. And then we define the inner product f comma g as the Riemann integral from negative L to L, f of x times g of x dx. So the theorem is that the functions sine n pi over Lx and cosine n pi over Lx for positive integers, and the constant function are orthogonal with respect to this inner product. And their squares, right? So if you calculate sine with itself and cosine with itself, as you can see from this integrals, is equal to L, are equal to L. And if you take 1, the constant function, and integrate it over the interval, you're going to get 2L. So let's check some of the assertions of this theorem. So compute integral of sine n pi over L times cosine m pi over L. So the theorem says that this is equal to 0. So if n and m are different, this is equal to 0. Now, why is this true? Well, the integrand is the product of an even function with an odd function. So it's not surprising, right? So the integrand is odd, and we're integrating it over the symmetric interval. So hence odd, and we get integrate. So we get the function is odd. So the integral is equal to 0. Now, how about two signs? So if you integrate, it also says that if you take sine n pi of Lx times sine m pi of Lx, you're going to get 0. So to establish that, we need to use one of the trig identities. For example, the one with the cosine of the sum of two arguments. And then we convert, so there's a negative sign here. So express this from substituted to the integrand, and you'll get this difference of cosines. And then when n is equal to m, so the first coefficient is equal to 1, and the second coefficient, and here, so the integral yields L because there is a 1/2 here, and the second coefficient is the term integrates to 0 because it's a periodic function. So recall that in the inner product space, the orthogonal projections of a vector v to the space spanned by the vector w is given by this formula. So we take inner product of v and w divided by this absolute value of the length squared by the length squared of v and multiply by w. And given an orthogonal set w1, w2, and so on wn, the orthogonal projection of v to the space, the span is given by this linear combination with these projections as coefficients. So if wi's were a basis, then this is the expression of vector v in that basis. So now let's apply to this to the orthogonal set that we have just found. So if a function with domain negative LL, then its Fourier series looks as follows, right? So the first coefficient is integral of f from negative L to L dx over 2L multiplied by 1. And then there will be a series, an infinite sum of cosine n pi over Lx multiplied by this coefficient, which is integral over f with cosine and n pi over Lx, plus another series where the coefficients are integrals of f multiplied by sine n pi over Lx, and everything is divided by L. So just again, look at the here. So those integral coefficients are exactly these coefficients here in the linear combination, and W's are sines and cosines. They are vectors in the basis. Okay, so if you want to write a slightly less cumbersome formula, let's denote those coefficients with a and bn respectively. So an is 1 over L integral from negative L to L f of x cosine n pi x over L dx, and bn is the same with the sine. So the Fourier series looks like this, and a0 was the integral of the function itself. So this is the Fourier series of the function f, which is constructed as we discussed, right? So we think of it as a function that periodically replicates itself from all over the place through the entire line. Okay. Now, if we had been working in a finite dimensional vector space, it would have been true that these functions plus the constant give a basis. And then by orthogonality, the Fourier series would have expansion, would be the expansion in this basis. So in particular, a function would be equal to its Fourier series. In fact, this is true in this case as well. However, you need to impose some appropriate conditions, right? Because here the vector space formed by these functions of all values of n is not finite dimensional. And here's the theorem, which we're not going to prove, but I'm going to state it. So if f is a piecewise continuous on negative LL, then integral from negative L to, well, any value x here between negative L and L can be computed term-wise from the Fourier series. If in addition, the derivative is piecewise continuous, then the Fourier series converges pointwise to the function everywhere away from the discontinuities. And if in fact f is continuous, so if those discontinuities that we made up by patching together the copy of the function over the real line, meaning that it takes the same value at those boundaries at plus L minus L, and in addition, f prime is piecewise continuous, then the convergence of the series is uniform, right? So that it kind of uniformly happens on every point in every x in L. And even stronger statement, so if f is continuous, so there are no gaps at plus minus L, the derivative and the second derivative are both piecewise continuous, then the Fourier series for f can be differentiated term by term to get the Fourier series of the derivative, right? So in other words, take a series, take a derivative for every term, resum it, so and that the series will sum to the derivative. Let's compute some Fourier series coefficients. So take square wave. So it's like a function that with period 2 pi, which looks like this, right? It has the value -1 from -pi to 0, and then there's a gap. It's 1, like this, right? So you can write it like so. This is pi 0 -pi. And then there's this continuity here. So you can further continue it down like this. So let's find its Fourier series. We compute its Fourier coefficients using the formulae. Now, note that coefficients an vanish because of the parity, right? So it's an odd function. So every integral over the symmetric interval from -pi to pi would vanish. And Bns will give us the following answer. So since f of x is just the sign, it's -1 to either +1 or -1. So we would, and then using the, so since f, right, so if f is a -1 when x is from -pi to 0, and if +1 from 0 to 2 pi, we can convert this integral into double integral from 0 to pi of sine and x, and then, well, the antiderivative of sine is cosine, negative cosine, and then between 0 and pi, we'll get this answer. So the Fourier series is given by this. So there are infinitely many terms. 4 divided by pi, sine x, plus third sine 3x, plus fifth sine 5x, etc., etc. Now consider the periodic function with period 2 pi given by absolute value of x in -pi pi. And let's determine its Fourier series. So it looks like this, right? So this is the, if you do it from -pi to pi, and then as you might guess, we want to continue it periodically to the whole real line. So it looks like a saw, like a chainsaw, a handsaw. Okay, here are the expressions for the Fourier coefficients. In this case, b coefficients will vanish, right? Because this function is even. Right, so this integral is equal to 0. So also remember that there's a constant, right? Because this plot, this picture is shift. The graph is shifted above by what is it? By pi over 2. So we have this as 0 coefficients. So we need to integrate the absolute value of x from -pi to pi, which will give us pi squared. And the coefficients an with the cosines will look like this, right? So we need to integrate, again, using parity properties, we convert the integral into 2 divided by pi integral from 0 to pi x cosine nx, doing the standard integration. We're doing integration by parts rather, right? So you would do integration by parts here, and then do the substitution, which will give us again similar looking expression: 2 divided by pi squared, -1 to the n minus 1. So the Fourier series is given again by, so there's a constant term and the similar looking expression only now with cosines. Only also notice that because of when n is even, this expression, this in the parentheses is equal to 0, so that we only have odd harmonics present in the answer. So there's cosine x, cosine 3x, cosine 5x, but there is no cosine 2x, cosine 4x, and so on.